Good afternoon, good evening, good morning, wherever you are watching us on this planet. Today we are going to discuss about Tangra, a software to analyze, extract the photometry on occultation data. I know a lot of you have been asking about this, so I decided to do this video. And for this, I invited my colleague, Josef Hanuš. Hi, Josef.
Hello, everyone.
So Josef is a researcher at Charles University, at the Institute of Astronomy here in Prague, and he showed me basically Tangra working. And Josef is very known because he's one of the researchers working with our team on the development of the shape modeling for our telescope using light curve inversion, but also occultation data. So tell us a bit about Tangra. What is this?
So Tangra is a software for processing the occultation data. So it does aperture photometry of the stars and potentially tells you if you have recorded an occultation. So usually you have to start with the web page of Tangra, where you go to the download part and download the version that works very well for Windows. We tested that. We haven't tested the Ubuntu or Mac version, so that's up to you if you want to try. So after you install, you simply run Tangra and you open the files with the observations that I have in this directory, and because there is no dead time between the individual images, we can treat the FITS files as video. So we click on this, and we also use some
maybe before going through that, we should mention that
sure.
The data are being here. The data you get them are in fits. So can you tell the people how you got the fits file?
Yeah, I asked Franck Marchis, a colleague of mine that has access to the data, and I got the data from him.
Yeah. So what's important is that to get the data in fits format, you need to upload them on the Unistellar server. And at the SETI Institute, we have access to this data, and we send you the scientific data if you want them. You just need to tell us when you observe and the 6 digit of your telescope, and then you receive a link, an URL link. You click on it, and the data are being uploaded automatically on your computer. This is still a manual thing, but we are working on having something automatic, so you don't have to ask a human being like myself or another person at a group to do it for you, meaning that you can get the data as soon they have been uploaded onto the server. So that's going to simplify the life of everybody. So FITs are files that we use in astronomy. They have a header which contain information such as telescope time, when the observation was taken, from where, and so on. And then there is also the data itself, which are encoded in 12 bits. So tell us a bit about that now.
Yes, because Tangra now uses some information from the headers. It founds the date of the observations and in which format they are, and also it looks at the exposure time. In this case, it was 0.08 second, and this basically saves us some time because otherwise we would have to do it manually. And I think there is nothing else we should change here. So we just continue with the processing, and I think this is the first image that we obtained, and some information about the dynamical range in the image.
So here you can play with that to change kind of the display, so you can see more or less stars. That's what you're doing here. So you can see 2 stars on the screen, 2 bright stars, for instance. So one of them is probably the occulted star, so you know that.
Yeah, this one.
Okay. So let's select them.
Is comparison star. So we get rid of this frame and we just need to tell Tangra that we are analyzing asteroidal occultation here. And now we need to do some manual selection of the occulted star and some comparison star. So we know that this is the star that was occulted, so we add it as an occulted star. And it's important to have also a comparison star, which is this one. We can add it as a guiding comparison star, and we can also add additional
this one is good.
faint star as a second comparison star, because in this case we selected a very short exposure time of about 80 milliseconds, and only the brightest stars are bright enough to be seen in the images.
Okay, so the analysis is starting. We're doing what we call aperture photometry here. You want to explain briefly what's happening?
So basically, the Tangra, we can switch here, uses circle aperture, and it reads the number of photons or in the pixels that are in the circle, and counts
The flux.
And it does it for the occulted star and for the comparison stars.
So this in blue is the flux, the occulted star, and in yellow and green is the reference stars. So the aperture size depends of the flux of the star, but also the conditions. But Tangra is taking care of that by itself. That's the key part here. You don't have to do anything by use. Everything is done automatically by the software. And around the circle, we have an annulus that is used to estimate the background. So you have the true flux of the star. So it's finished. Let's see what happened.
Yes, here just Tangra uses some additional information from the headers about the camera, and the light curve should pop out, and here we have them.
So in yellow, that's the bright stars with a count of 300,000 roughly. In blue, the occulted star with 150,000 roughly. And in green, the faint star we selected on the end, which is extremely faint, probably less than 200 counts. So you're gonna remove this one, and that's more interesting, but definitely something cool here.
We can also mention the scale.
Okay, yes. What is the x-axis here?
Yeah, it's the duration of the observation, which covers about 30 seconds, and each point corresponds to one frame.
And the y-axis is number of counts. ADU is basically the number of counts in the aperture. Okay.
So during the time we were observing, there seems to be one dip, like significant dip in the magnitude.
Yeah, you can see the star completely disappear here. The reference
in this frame. The nice thing is that we can change, or we can move within the frames. So basically here there is nothing happening, and suddenly we have a dimming of the star and complete disappearance, and then again it's getting brighter and brighter, and then it gets to the normal brightness.
So this is an occultation. So to explain briefly what you have seen here is basically the star disappearing because an asteroid passed between you and the star, and the asteroid is 1989 EW. It's something we predicted in our Unistellar database. You were located, where were you?
I was located in Pilsen, in Czech.
In Czech, yeah. So you saw it.
Yeah, I saw it in the app when observing as a very short disappearance of the star.
It typically lasted, like I will say, between 200 and 300 milliseconds. Something remarkable is that human eye can see something disappearing if it's roughly more than 20 milliseconds. I would say even 10 milliseconds, but I'm not 100% sure. So that means that eyes are very good at detecting the disappearance of something and reappearance. And you saw it doing your observation live, and you send us the data, but the pipeline that we have at Unistellar currently is not able to detect such a brief disappearance of a star. We do some smoothing to average and to improve to improve the signal to noise, and in some cases, the smoothing make that the brief disappearance of the star is not detected by the pipeline. So you were convinced that there was an occultation, and that's the reason you use Tangra to extract yourself the photometry.
Yeah, that's exactly what happened. Because I was trying to convince Franck that there was an event, a positive event, and he was trying to convince me that
there was none.
There was none.
But I was wrong. There is an event. I mean, now by looking at this, it's clear that there was an event this night when you observe the occultation.
Yeah, the main problem is that the Unistellar processing pipeline is not developed to detect these very short events of just 1 or 2 frames. Unfortunately, these events are quite common because most of the asteroids are small.
Mm-hmm.
So these events are very common.
So why are they important?
They're important because if we succeed, if we beat the odds and beat the very low probability, we can measure quite accurately the position of the asteroid and use it this refined position to improve the future predictions of the occultation by this particular asteroid, and then we will have much higher probability of being successful in measuring the occultation.
Yeah, so basically this is a 2 or 3 kilometer body, probably. The uncertainty is probably like 20 or 40 kilometers. So the odds of detecting this is probably 1 or 2%. And you detected one of the event. As soon as you detect the event, we know precisely where the asteroid is located, so we can recalculate the orbit. And from that, later on, we will be able to predict more accurately even if there is a new occultation. And what's interesting in this case is that the more people observe an occultation, the more chords we have and positive chords we have, the better we can estimate the shape and the size of the asteroid. So that's one of the projects we have, is to really be able to, in the future, to derive the shape and size of multiple asteroids, a large number of asteroids, even the smallest one, like the 2 to 3 kilometer in diameter. So we will change the pipeline to make it better, but we also need to have more observers making those kind of observations. And then what's the next step? Now we know we have an occultation. What are you going to do?
Yeah, the next step would be to measure the disappearance and reappearance of the star. To do that, Tangra is not sufficient. It's not developed to do that. But there is an additional software called AOTA that allows you to analyze the light curve that we just created by Tangra and measure and fit the occultation profile, fit the occultation model to estimate the disappearance and reappearance of the star, and thus the duration of the occultation, which is directly related to the size of the object.
Alright, excellent. So that's going to be the topic of another video, I'm assuming?
Well,
I'm staying here for 2 days, so we have time to do that. Okay, so we're going to have a next video in the future with Josef, where we're going to show you how to do this extraction of how to derive the profile of an occultation using IOTA. But for the moment, I recommend you download Tangra and you try yourself at home when you have an occultation, recording an occultation, so you can also check if you have detected one of those brief occultations.
yeah, I would be happy to show you how to process the light curve with AUTA in the future, and I hope that at least some of you will use their telescopes to observe some of these events and help to contribute to the asteroidal science.
All right, thank you. Well, see you next week, maybe, or another time with another video. Thank you again, Joseph. Bye bye.
Thank you very much. Bye bye.